This is LeetCode problem 146 LRU Cache. Design a data structure that follows the constraints of a least recently used cache. Implement the LRU Cache class, including three parts. LRU Cache initialize the LRU Cache with positive size capacity. Get, return the value of the key if the key exists, otherwise return -1. Put, update the value of the key if the key exists, otherwise add the key value pair to the cache. If the number of keys exceeds the capacity from this operation, evict the least recently used key. The functions get and put must each run in O(1) average time complexity. Let's look at an example here. Put 1 100, put 2 250. The cache is 1 100, 2 250. Get 2, return 250. Put 4 300. Cache is 1 100, 2 250, 4 300. Put 3 200. Cache is 2 250, 4 300, 3 200. At this point, it already reached the maximum capacity, which is 3. That's why we evict the least recently used node and add 3 200 as most recently used node. If we get 4, then we return 300. We get 1. At this point, 1 is already evicted, 1 adding key 3 due to capacity, so we return -1. Let's visualize the problem. Least recently used cache currently holds 3 elements and has reached full capacity. Key value pairs are ordered from the least recently used to the most recently used. If we try to put a new key value pair into cache, this new pair would effectively be the most recent used in cache. It should be added at most recently used end of the cache. If cache is currently at maximum capacity, we need to evict the least recently used pair. It involves 2 operations. One is to remove a key value pair from the least recently used end of the cache. The other operation is add a key value pair to the most recently used end of the cache. For getting a new key value pair, accessing a pair will make it the most recently used pair, so we should move it to the most recently used end of the cache, and also return the value. So in this case, get 2, we move 2 250 to recently used end, and then also return 250. For get function, it involves 2 operations as well. One is to move a key value pair to the most recently used end of cache. The other one is access a value using its key. For operation 1 and 2, we need the ability to move a key value pair from one end of a data structure and add a key value pair to the other. A suitable data structure for these operations is a linked list. Should we use singly linked list or doubly linked list? In terms of adding or removing a node from the head of a linked list, they both take O(1) time. In terms of removing tail node, doubly linked list takes O(1) time, singly linked list takes O(n) time, so we should choose doubly linked list to be more efficient. We need to access both ends of doubly linked list when adding or removing nodes. The head of linked list signifies the least frequently used node. The tail of linked list signifies the most recently used node. To reference the ends of the linked list, we can establish head and tail nodes. Head points to the least frequently used node. Tail points to the most frequently used node. For operation 3, we need to move a node to the most recently used end, and this node doesn't necessarily need to be at the head or tail of linked list. If this node is somewhere in the middle, we need to traverse linked list to find it. Since this node is associated with a key, we can use a hash map to store key value pairs. This allows us to access a node by its key in constant time. For operation 4, using a hash map also addresses access to values from their keys. This is the flow for adding a new key value pair to cache. Is the key already in the cache? We should check by querying hash map. If it is yes, then we should remove this key's node from linked list. Add the node at the most recently used node of linked list. Add it to hash map. If the key is not in the cache yet, then we should think about if we add this new node, will that result in exceeding capacity? If it's no, then we should just add the node at the most recently used node of linked list and add it to hash map. If it's yes, then we should remove the least recently used node from linked list, move it from hash map, then add the node as the most recently used node of linked list, add it to hash map. For put function, we need two helper functions. One is to remove a node, the other one is to add a node to the tail of linked list. This is the process for retrieving a key's value from cache. Is the key already in the cache? We should check by querying the hash map. If it is yes, then we should make node at this key the most recently used. Remove the node, add the node as the most recently used node of linked list, and then return the value associated with this node. If the key is not in the cache, we just return -1. How can we achieve add to tail function? Let's say in this example, we wanna add node 3200 to tail. We should first refer the node before tail as previous node, and then we set new node points to the previous node, set new node points to the tail node. At the end, we set previous node points to the new node and set tail points to the new node as well. This is the coding part. How do we achieve remove code function? Let's say in this example, we want to remove node 4300. We should set previous node points to the next node and set next node points to previous node. This is the coding part. Now let's code it up. For the first class, doubly linked list node, we need to have key, value, and a reference to next node and a reference to previous node. For the class least recently used cache, we break them down to 5 sections. The first one is to initialize capacity, a hash map that maps keys to nodes, and also the head and tail dummy nodes. From there, we connect them to each other to establish a basic 2-node doubly linked list. We already covered add to tail function, remove node function. For get function, if key is not in hash map yet, we should return -1. If the key is already in hash map, then we should remove its node first and then re-add it to the tail of linked list to make this key the most recently used. Eventually, return this value. For put function, if a node with this key already exists, we should remove it from the linked list. If a node with this key does not exist, we should add it to linked list and hash map. If adding this new node will result in an overflow, we should remove the least recently used node from the cache first, and then add node to tail as most recently used node. Time complexity is O of 1, space complexity is O of n.